Hello and welcome to e-lecture 13 from the EGM37 Additive Manufacturing module. In this e-lecture we're going to talk about the design and build for considerations for additive manufacturing. We're just going to remember from the process control the general additive manufacturing process. And then we're going to look more specifically at design rules. So the geometry of the component, the placement of the part on the build plate, and then taking into account considerations for final machining. So if we recall, and you will have seen this a few times now throughout the course, additive manufacturing is based upon starting from a 3D CAD model. We need to convert that CAD model into a format which is acceptable for the slicing software. Typically this is the STL. After we've got the STL file, we will need to slice it into a series of layers. We'll need to add support structures if these are needed. Sometimes you can build it from the plate, as you can see on the example on the right there of this rather complex interlinking set of cubes. You have some supports which attach to the base plate, and then you have some internal support overhanging areas. We need to orientate the part within the build envelope to ensure proper build, maximize the yield from the entire build. We also get the choice of deciding on the build times, so the laser speeds and the laser powers, and all the material machine properties that we've discussed at length in the process control. This will determine the accuracy and the strength of the material. When this is done, the software will build a machine file, typically called for the Renishaw systems. It's the .mtt file, but it's a file which has a description of the entire description of the movement of the laser throughout the entire component. This is transferred then onto the machine, and at this point we start the build. So starting from the base plate or the base platform, and a layer at a time, which is very important. It's built sequentially, one layer at a time. And at this point, there will be a variation in how the build is done throughout the different additive processes we've discussed. Blown powder, so the powder gets blown down through nozzles that intersect just above the build plate. Wire can be laid with various heat sources, be they arc welding or TIG weld or electron beam. The powder can be laid on the bed in the powder bed systems. And of course, there's also wide variations of the type of materials. So metals we've mainly discussed a lot in the course, but in the same way, powder bed for polymers will work. At this point, would be a different type of build. When the build is complete, we have to remove the build plate, and we have to remove the support structures. And at that point, we will decide what post treatments we will need to do to finalize the component, whether that be heat treatment such as hot isostatic pressing to remove porosity in metal parts, or heat treatments to reduce residual stresses. Also, you need to consider things like polishing the parts to remove roughness, that be through sandblasting, shot peening, vibratory trough cleaning, all different types of cleaning. Then of course we will also have, what I haven't added on here, but we'll also have the post-machining steps, drilling holes, possibly adding threads and all that sort of stuff that comes afterwards. So this is the basic generic process which underlies all additive manufacturing processes. So what kind of software do we have for the slicing, particularly? So for the CAD though, on the CAD side, we have CAD that produces STL, so you're very familiar with SolidWorks, Pro Engineer. You can get lots of different freebies, SketchUp, FreeCAD. that actually produce perfectly usable STL files. The STL files is not possibly the best format that could be used. STL is a very simple file format, which has a series of triangles which covers the entire, meshes up the entire surface. But sometimes that simplicity itself is this downfall, that a triangle can be missing and you end up with an open volume, and there's no volumetric definition within the STL file. So sometimes you need an intermediate piece of software to fix the CAD. So I've just mentioned a couple here. There's a NetFab, which has a free version. There's MeshLab. There's GeoMaterials. There's a lot of CAD. Rhino, for example, can also do fixing of STLs. So the next stage, though, is the slicing. So if we're actually specifically developed 3D printing software, so there's Materialize, there's Magix, Markham, AutoFab, all these worth looking into. The operation of the 3D printing software is sort of, as mentioned slightly before, you pull in the component with the STL, and at this point you're allowed to so you can rescale it, shrink it. You can compensate for shrinkage for the machine. You could at that point then you can create slices and decide how the slicing is going to work. You can put your support structures in here. It'll subdivide down, and you choose your hatch pattern. So here you can see the laser tracks themselves and how you're going to actually do the hatching on each layer, and then it creates the job file, the build file, and that's what is exported to the machine to build. So I'm going to kind of summarize some of the work that was done in a paper, which I'll give you more details on in a bit. But generally, the part design will come down to three main considerations. First of all, the geometry itself you have to consider. You have to consider then how you place the part on the platform. And then also you have to, before you, when you're actually designing the part for AM, you have to take into account considerations for the final machining. So within the general geometry, okay, that will be determined very strongly by its size. So as you know, a pretty standard powder bed size is 250 millimeters square base, with up to maybe a 300 millimeter height. With some machines, newer machines coming out with larger sizes, but the size, how high it goes, how many layers you're going to need, this is very important. It'll determine how you can orientate the part within the build. The thickness of the walls and how they are orientated with respect to the build, that's very important. Features, holes, bores. Some of these features you can build directly, maybe without even having support structures. Others you may choose to defer to a final machining step. One of the things that you will have seen a little bit about, and we talked quite a little bit about during the module so far, is overhangs. So these overhangs are what determine the support structures that are required to hold them up. And this is probably the single most complicated part of setting up a build in a powder bed system, for sure. But it's generally the same problem across, whether it be for polymers and or for any of the additive wire arc. There are certain overhangs which just cannot be made without a support structure. Right, placement of the part. So the alignment of the part can have an effect upon the surfaces, surface roughness. How we align the part and place the parts within it can minimize the number of overhangs on a specific geometry. It also, of course, that the part placements are important for the economics of the process. So the more parts that you can place in a build, so therefore with the packing density, this needs to be done sensibly and with minimum interference from one part to the other. So finally, the considerations for final machining. So of course we need to take into account the allowable tolerances of the part and what we can actually achieve. We may have to compensate in the part if we know that there's going to be some distortion or geometrical shrinkage. We may have to consider that in the build, and we will also have to decide the best orientation of some of the parts in order to maximize the efficiency of the polishing steps and the improvement of the surface quality. So again, that just breaking down now the general geometry considerations into a few more detailed steps. So the general part size, height being the most important. Certainly, you may be constricted by the amount of powder that you have available in the hopper, and we'll see this a little bit more when we talk about the powder feedstock. You may be constricted to 100 mil height because of the amount of powder you've got, or you may have enough powder to be able to do the entire height of 300 millimeters, but that has to be taken into account. So cavities, one of the things you have to consider, for example, with cavities is the fact that you're dealing with powder, and the way the process works, you can incorporate a cavity quite easily within the geometry, and you will actually be able to have the outline surface of the cavity, but the powder will be retained within that cavity, and there will be a level of surface roughness. So if those cavities were, for example, to be cavities in tooling for cooling purposes, you would have to think carefully about how you are actually going to be able to remove the powder afterwards. So really, there can be no enclosed cavities without consideration of how the powder has to be removed. Okay. Other things, okay, the design, that's what we're talking about. Volume, the powder removal I've mentioned already. Walls, so thin walls sometimes may not build so well, and you have to take into account the way in which we design the edges and corners. Will, in terms of a design plan, we want to be able to incorporate the build in such a way that if sharp corners, if you can avoid them, much the same way as you would do with a powder metallurgical process like powder compaction, sometimes if it's not part of the design, then rounding off corners is sometimes better for a build in transitions in the vertical direction. So more things to consider in terms of the geometry, bores, how they can be built into the part design, beams, the gaps. There is a minimum gap, and we'll see some of the examples later on, but in general, you will not be able to achieve any significant beam gap resolution which is less than 3 times or 4 times the beam diameter. After that point, the quality of the gap is very poor. Circularity, because of the shrinkage and the attachment to the plate, circles, ellipses, cylinders, hollow cylinders can have a significant level of distortion, and it is actually quite difficult to compensate for that distortion in order to get the absolute circularity that you want of the part. Support structures, the big thing about with support structures, you need to be able to attach support structures so that they are, and probably the most important thing is that they're easy to remove. So therefore you need to have access to them for however you're going to do the detachment of the support structures. If it's going to be done by hand, picking off, or as maybe using a Dremel, but nothing major, then you still need to consider how you're going to get in underneath the overhang, where you need to remove the support structure. And if it's going to be done by a machining process like electric discharge machining, that same process has to apply. So when you are actually putting the plate on the part onto the plate, you need to consider that. The way in which supports are attached to the part is important for their removal and making sure that they don't damage the surface during the removal. This critical angle is mentioned here is that 45-degree angle at which lower angles of overhangs will be critical and need support. It's not always the case. Sometimes if you have small enough holes, they will be self-supporting, but certain features as they go up, the overhang becomes big enough that you need the support structures. So now looking down the part placement, this is just basically going through what we've already talked about, so I'm not going to go on any more about that. So with all the design, the best way really to understand the design at the moment is to go through a series of test builds, which allow you to link up the material that's being used with the additive process which is being used with the feature geometries. And we have a series of very standard tests that we have test plates, and we'll put them on. We will look for material properties like density through parts which look similar to this. We'll look for the surface finish and density, and sort of with parts like this. We'll have some holes in it to see how well the holes have been made. We'll look to see for the dimensional accuracy. You might have an annulus form like that. To test the overhanging area and the capability of the overhanging area, particularly from the perspective of what happens to the surface roughness as the critical angle is tried. You can see various shapes that may which will be testing the level of accuracy of the build in a vertical direction, and these can then be checked with a backlight system. More intricate little components that get built, which may give you the potential of looking at various tests all at once. And then of course you've got your sort of material based tests where we've got tensile and fatigue bars that can be built. And hardness being a relatively easy one to do, you could probably try just on the same cubes that you use for the density. So you might have during a build campaign, you might have a simple plate with these kind of components on it, which is built every few builds, and it checks, well, first of all, that you are achieving what you want in terms of the build quality, the geometrical features, the accuracy at the beginning of the build for a first one-off material. But then of course you can incorporate these builds every few times into your build campaign, maybe every 5, 10 builds or 15 builds, just to check that there has been no misalignment of the laser or anything has changed in the process, and then you're still achieving the same results. Here's a rather poor quality image of some of the standards test pieces. So you can see horizontal test bars, you can see some angle test, probably to check the surface roughness and the build quality. You can see this at the angles below 45 degree that you've got a various poor build qualities there. This is just another one. It shows some tensile test bars at the back and various small test pieces which are used for, in this case, thermophysical property measurement. The standardization is something which is being worked on by various projects, and this is just a summary of some of the components which are being used for standardization or proposed for standardization by a project called Amaze, which recently finished last year. And you can see in this case that you've got sort of looking at on rather larger blocky structures, just to see how accurately they're being built. Concentricity here, as I mentioned earlier, you can then use a CMM machine to measure the location of the inner wall and the outer wall, and you can compare that to what it was meant to be. So here are slots, a series of smaller and smaller slots, just to see how small you can go with the slots. Holes in a vertical direction to see what's the minimum diameter of a hole and how well that gets resolved. So these ones here with a 0.1 mil or 100 micron, 200 micron are the challenging ones. Okay, so all of this resolution here is extremely challenging for any system and will give you the lower limit of the precision. The same with vertical upstanding cylinders here. These ones here, which are the 0.1 build, you will be lucky to be able to build. A mesh and a lattice and a series of smaller and smaller lattices, again with very small walls, and that will push the machine to tell you how accurate you can do. Post checks, so it can be done on all of these parts. Here we've got another, which is particularly what we're interested in. It's not just the surface finish, which we could do tests on these, but also whether they actually successfully build or not. And in order to put this part on the plate as it's looking there, you will have to put support structures here, here, but some of these will self-support. Okay, and it's not necessarily 45 degrees, so finding that lower critical angle is important. So there's another best case there for very much the same thing. Here we have something which we're doing, looking at the surface roughness on both sides, can be measured with a probe afterwards. Determine that. So this was the paper I was mentioning before by Kranz in 2015. I thought it was an excellent paper which looks at the sort of more design guideline side of things, and they go through a series of examples of what is a good practice and what might be bad practice in putting a part together. So a lot of the design guidelines which I am offering you here as part of this lecture are in this paper, and I would encourage you to go and have a look at it. There's the reference down the bottom here, which you'll find on the slides, and you can see. And I'm not going to go through every single one of them. I'll pick out a few as we go along that I think are of particular interest. So what they're saying is, use, in this particular case here in terms of the volume, they're saying if you can incorporate cavities into design, this is part of the beauty of additive in the first place, is that if you've got volume of material which is there, not because of the functionality of the component, but rather because of the way that you manufacture at the end component, if you can reduce the weight, reduce the material, you're taking away the manufacturing time and obviously reducing the costs. So this is an extreme positive side of what you can do, but you have to do those with consideration of how you can actually achieve it. Corners, if you can avoid in your design sharp corners, and you can round them off, this will actually reduce the thermal induced stresses and will actually, in some cases, help the build if it's going in the vertical direction. Cavities, but always considering the removal of the powder afterwards. Okay, so you have to have an opening that allows you to get the powder out. We made this mistake and I've shown you this in class, was the turbine blade. We tried to make hollow, and then we realized only afterwards that we hadn't thought of a good way of removing the powder. We've talked about the staircase effect as well during the process control. So this is the actual the limitation of the process, where we have a discrete layer thickness as we go up through the build, and to that extent we need to avoid, this is going to result in a surface roughness which is inherent to the process, and we have to think of ways that we can minimize that. So the orientation and the curvature of surfaces cannot be too extreme to a certain extent, otherwise you'll end up with the staircase effect. And this also applies to holes or bores that you design in. So you can see two examples there where you're losing material from where you wanted it, and you're gaining material where you didn't want it because of the staircase effect. So there's a lower limit on the sides of the holes that you can leave, and there's also an upper limit because of the fact that you're going to need support structures in there. When designing bores or holes in material, this is something that we have already talked about. If possible, where possible, if your hole doesn't have to be cylindrical, so don't believe that if you're coming from a machining background and everything gets bored in by you're drilling, then it makes sense to work with circular bores. But does that necessarily need to be the case? So if you're designing a cooling channel, does it necessarily mean that you have to have a circular cross section of the bore? Probably not. Now, if you use a teeted or cross section of your bore, it means that you can probably get away from having to put support structure for larger holes. Yeah, and you've got to remember here with this particular machine setup, which is for a concept laser, 12 millimeters, and this data would only come from trial and error. 12 millimeters is the maximum diameter of a bore that can be used without the necessity for support structures. But you can greatly increase that diameter by using a self-supporting teeted build over the top of the at the top of the hole. And the same goes for sort of arches. And if you can build in sort of elliptical, that has the least requirement for support structure. Okay, so that's one of the points I wanted to make from that slide. We've had this one already, and okay, so gaps. We saw one of the benchmark standards where you can determine this with a pre-build, that they actually point out that the minimum gap for their machines with titanium, which is quite a good powder to work with, has a very good build quality. Their minimum gap size is 0.2 millimeters or 200 micron, which is very similar to what we find with the Renishaw machines with DI64 as well. Overhangs need to be supported, so the consideration of the support structure is important. We've talked about the support structures within holes. Overhangs over 45 or 50 degrees are necessary. So this critical angle for these particular machines, yeah, that if the angle is above 50 degrees, which where they're measuring it from the vertical, so that means that they can go down as low as 40 degrees from the horizontal. There, they can have a 40-degree angle there. They will be able to build on, but anything which goes more horizontal than that means you absolutely need support structures. They have so there's a range between a 50 and 80 that they're definitely, once it's above 80. So, but there is a small amount of leeway that you've got. And that always depends upon how much post machining you're going to do anyway. So obviously, if you're going to have support structures, you have to have them laid out, and you have different types of support structures, and they need to be considered. So very much the connection between the support structure there and the undersurface of the overhang. So if you're going to try to remove it by hand, having a very small connection point there is favourable. If you're going to be able to machine it afterwards, you could possibly have a more robust connection between the support structure and the overhang. But then you're going to have to make sure that you can machine that off if you need to have a smooth surface there. Okay, the part placement itself will affect the quality of the final surface roughness. And this needs to be taken into account if you're going to be machining or polishing it. You need to have the quality of your part afterwards. So, yeah, as I said, this test was done on 2 different machines, a Concave laser and an EOS machine, both with the same powder. They have various differences. It's all in the paper. It's very interesting. This is quite an interesting point here, which is about, and it relates to the sort of packing density of, how closely you would locate parts. So here, they built a series of cylinders on the plate, and they recommend that the distance between them should be no less than 5 millimeters. That being because you can have thermal interference between the cylinders as they build, but you can also have, as the parts are built, you have gas coming down, and it takes away the spatter and the condensate that can settle on the part next to it. So you could actually have the downstream cylinders could potentially be having inclusions from the upstream parts, so they could be interference. So they recommend 5 millimeters. I would actually say, if possible, that's not enough. So for bigger parts, this is very much a try it and see sort of. There's no hard answer, but I would say 10 millimeters to be safe in some cases. So now we've got a few real examples here. This is by a chap called Daniel Thomas, who did his PhD at Cardiff. So it's a little bit out of date in terms of the quality you can get. So you can see here that at this point in time on the machine they were using, they were struggling to get any sort of definition of holes less than 0.5 millimeters. So 0.2 millimeters is much closer to the sort of level of accuracy that we can achieve in our machines nowadays. But this kind of comparison is still very relevant, and I think particularly what I liked about the work that Daniel had done on his thesis was the sort of systematic working through of the achievable geometries. So you can see, for example, here that as you reduce your hole size, you start to get this interference and lack of precision that is at their point on this machine was visible by eye, but this was much more acceptable as you went up to 2 millimeter. Talking about these self-supporting peaks that allows you can see here some of the holes achievable with the peak. So 4 millimeters and 13 millimeters are actually looking very accurate indeed, and this is on the old system, and you can see that they went up to quite significantly large self-supported internal cavity structures. So this is an important thing from a design perspective as a proof that if you can incorporate this type of supporting cavity, then you should use it. Daniel proceeds with a series of other tests very similar to what we've done, and as you can see the lower accuracy is a lot worse than it was in 2009 than it is now, where 0.1, 0.2 is much more achievable with the new machines. He talks about the various radii, maybe a slightly different way of thinking than you would do if you were sort of machining it out. The wall thickness, here actually achieving The 0.3, 0.4 was at the very upper limit, so as we say, we can probably get down a bit better there with the wall thickness now. Just to conclude this chapter here now on the additive design, I'm going to go through a couple of examples, and this will show you a way of putting together a manufacturing feasibility report, which would be part of any design, product design using AM. So what we're going to look at is a relatively simple component, which was part of the Amaze project, which finished last year, and it is deceptively simple. It's a T-section, which was 240 millimeters long, and it had a wall coming up, which was 6 millimeters wide, and a 60 millimeter base. And this was to be built in titanium 6-4 alloy. So what we're going to consider here is 3 different orientations. So one is building it directly on the base plate there. We're going to consider a 45-degree angle to the base there, and we're going to think about talk about how we would locate support structures on this. And we'll also talk about this third option, which is to have a vertical build straight up. Let's talk about the first case. So in this case, we needed support structures everywhere on the base. But what we can notice already from experience, that this is going to mean that we have a thick forest of support structures located everywhere below the base wall. And you can see a picture of them here. It's a very large surface area, and for a relatively thick component, which means that we are going to possibly have a lot of residual thermal stresses induced, which will lead to obviously high residual stresses within the part, but potentially, well, if we look at some of these videos, you can see the build plan as a series of every few layers we pick them out. And you can see in the first instance the support structures being built up underneath, and that goes into the main base of the part. Each of these yellow lines, which is very difficult to distinguish, is actually the laser path is defined. You're going up now into the wall being built up. So that's the theory. Now, what happened in practice? Well, the thermal stresses were so high that they managed to tear the part during the build. And you get this classic thermal stress banana shape, where the ends are trying to push out through the thermal expansion, and then as it contracts and cools, it's pulling away. The weakest point is at the point between the support structures and the part itself, and that's where the tear has initiated. And I think to a certain extent it's quite a slow incremental tear has led to this crack looking larger at the end, and obviously a relatively unusable part. But what we can also see is that the machine didn't break down and stop while it was working. It kept on putting layer upon layer upon layer until it actually self-corrected itself. And if you this looks a bit, it's actually incredibly flat and exactly in the location that we meant to build it here. So you can see a feature of the machine that has actually corrected itself through the build, even though it's failed there during the build. At this point, the layers have kept on building and they're back where they were meant to be. So here are some more pictures, but the final outcome is that this part built like this failed. Right. Move on. Can we use the inherent critical angle? If we can work at the 45-degree angle, surely these surfaces should build as we go up through the build. And we will need a minimum amount of support structures because we're told that it should be able to build in these 2 directions. So can we use this minimum support structure on the right? That's the question. What can we anticipate? Well, we're not quite sure, but these walls are relatively thick, and it could be that they need to have heat drained and these support structures are not creating enough heat drain. So let's have a look at the video. An idea. There's the support structures being built and the first part of the component. So the support structures come up as you go through the build. They join the component, and then you see the component. In theory, that's what we want to achieve. Now, in practice, what really happened was disaster. Okay, so you can see here it failed relatively critically because this actually took out the wiper and it stopped the machine from building. It was unable to build the component in any accuracy whatsoever. The support structures tore off at this part here. There was a little bit more success on this part here, but you can see there's a lot of distortion in the part. So the idea of being able to use that critical angle is and to minimize the support structures is only true to. Okay, so right, let's look at the last case here, and maybe this is the case that we should have started with first. So the orientation of this is vertically upright. In this case, the supports are not strictly necessary. You could potentially build a part vertically off the plate without any supports, but then you're going to have to cut it off. So if you have access to the electric discharge machining that we do in the workshop, then that's a relatively easy job. But let's have a look to see. We will make it in this case without support structures. So in this case, it built vertically upright without a problem. Now you can see that as in comparison to the first case where we had the wall of the plate plastered onto the base plate, and you can see the failed one in the back there, the area which is hot is significantly smaller because it's just the cross section of the T-bar. So therefore it has plenty of time to cool down, and at each recoating of the powder bed, and this built up without any problems, and in fact without any significant distortions. It's not always that easy to on more complex parts to decide which is the minimum cross-section area to give you that thermal stress, minimum thermal stress. So what we can conclude from those three examples there is that thicker sections and walls thermal stresses determine the orientation of the part very strongly. So we don't only have to avoid the failure during the builds, we also have to think about the distortion of the parts afterwards. The minimization of the cross-sectional areas will allow the part to cool down during each of the wiper. So the impact of the higher thermal stresses will be minimized. Orientations with minimized support structures are not always successful and may lead to distortions. That's a very clear case. So putting things at 45 degrees and taking the critical angle should be taken with a pinch of salt. So yes, it will help in certain cases in small parts, but when on bigger areas, it's not necessarily to be successful. Let's have another look at another example. So in this case, we've just got again a metal PI64 part with a series of different holes. It's just a flat plate with 3 holes basically drilled out of it, not necessarily something you would make for additive. It's about 75 millimeters long, 45 millimeters high, and should be 60 millimeters wide. So we're going to consider 3 different orientations of this part on the base plate. The case 1, we're just going to build it vertically upwards. Case 2, we're going to lie it down horizontally, and case 3, we're going to put it on its side. Right, so if you remember from the design rules that were published by Krantz, and I discussed it earlier on in this lecture, we will only need to have support if the if these holes have a larger than 12mm diameter. So case 1 and case 3 have the holes built in a vertical orientation. So certainly the larger hole will need support structures. And as we mentioned in terms of the design, if the shape of this hole wasn't critical to the part, then we could consider a tear-shaped hole. Okay, so now the trade-off here now is then to consider, for the wall thickness and face orientation, is a trade-off between minimizing the distortion and maintaining the accuracy of the holes while minimizing post-build operations. So a good structure to look at a manufacturing report in terms of the additive manufacturing is laying it out in a table. So we have a series of considerations that we might want to take into for each of the different cases of the orientation. The ease of removal from the plate. So case 1, which you can see down here, will result in a series of support structures which result in a relatively easy removal from the plate. There might be a couple on the connecting to the bottom, and maybe a few in the hole. So it's definitely going to be, one is going to be the easiest to remove. Case 2 will have a lot of support structure underneath the part, so that will be the hardest in terms of the removal of support structures. And case 3 will be somewhere between the two, but we'll still have quite a forest of support structures underneath there. So that would be the medium case. Now, distortion from thermal stresses. Building in this direction upwards means that the cross-sectional area is relatively small. It's probably the smallest, so the distortion I would expect to be lowest of 1. Case 2, we've got a relatively thick area with a lot of surface area along the plate, very close together. There'll be quite a lot of relatively high thermal stresses. We could see the kind of, if that is sufficiently thick, we'll probably see that cracking that we saw with the T-section that we considered earlier. And 3 will also have a relatively low thermal distortion as well. Now the concentricity, by building circles in the vertical direction, as in 1 and 3, we end up with relatively low concentricity for the accuracy of the holes. Now, so for the concentricity perspective, actually 2 is probably going to be the best, with 1 and 3 being the same poor. Now, the amount of support structures we've already mentioned here, 1 and is probably the lowest, followed by 3, and then the highest amount of support structure would be number 2. Surface roughness will be relatively poor in both 1 and 3, especially the surface roughness, not so much of the flat outer area, but the internal surface roughness within the circles will be quite rough. Much more so than in 2. So if we're talking about the surface roughness in the holes, so therefore the internal surfaces, which we're actually here, surface roughness of the external surfaces is actually the other way around. It won't be so bad in 1. 3, the end curvatures could be a bit poor. 2 will have relatively good surface roughness, except for the bottom face where we have to remove the support structures. So that would definitely mean that we'd have, in addition to cutting it off, taking off this, we'd have to remove internal support structures for both 1 and 3, which wouldn't be needed in 2. Sandblasting and polishing would be needed for all 3 of them. So that concludes the lecture 13. There's going to be a test on Blackboard, test 13 to go with this, which I would ask you to please have a go at. This now kind of takes us to a milestone whereby you have probably sufficient information to undertake your practical project. So what we're going to do is go through this in a summarized, condensed form in the seminars, and then we will also move on to some other subjects, such as the physics of lasers and sort of more academically difficult areas of the course. Okay, so I hope you enjoyed. All the best. Talk to you soon.